Hi kids, sorry for the unexpected absence, but I thought it was a good chance to try out a flipped lecture. In other words, I record the lecture and you guys can just listen to it on your own time. When you're done, I put a written and oral expression assignment on thermodynamics on the website, so you should try that, and I will read that and give you feedback when I get a chance. And if you finish that, then please move on and work on some of the multiple choice or FRQs. This is the last lecture in thermodynamics, so you should have information to solve many of the problems. I will say that the multiple choice problems that I've posted online are from the old APB exam, and some of them are not from the AP2 same structure. So if there are questions that you don't feel like you know the answer to, perhaps that's because we haven't covered the material because it's not on your test. So anyways, without any further ado, thermodynamic cycles. A quick recap or summary of PV graphs. Whenever you have a graph of the pressure versus volume of a sample of gas, you can use the pressure and volume values at any point of that graph to solve for the temperature and the thermal energy at that point if you already know the number of molecules. If that gas sample's pressure and volume change, so we have a thermodynamic process of some kind that happens to it, the thermal energy, or U, probably will change unless you're on an isotherm. If you're on an isotherm, the temperature stays the same, no U change. But any other path, you're going to have a change in U or delta U at some point. However, the U or delta U do not depend on the path it takes. It just depends on where on that graph it starts and ends. Compare and contrast to the values of work and Q, those do depend on the path, and you'll eventually be using the first law of thermodynamics to solve for all of those values if you can find a couple of them. You can often find the work using the area under the curve of a graph. That'll usually be a nice square graph to make your life easy, at least in AP Physics 2. And the one thing to make sure that you keep an eye on is if you're calculating that area, remember that if the gas is expanding, so the volume is going up, we define that as a negative work on the gas. It's doing work on the environment. Or if the gas is being compressed, the volume is going down, then you're going to want to put a positive sign on whatever work value you calculate. So the last little piece of this unit has to do with thermodynamic cycles, and it's basically a combination of two or more processes that make a closed loop. This is considered a cycle because the gas is returning to the same equilibrium state that it started with. It's going to have the same pressure, volume, temperature, and thermal energy as it did when it started. So it's in exactly the same situation or equilibrium as it was at the beginning. So even though the U hasn't changed, because U is independent of path, the work and the Q may be different from each other or different depending on the path that we take. Specifically, we could solve for the work during this cycle, and so one of those pathways, like for A, you would calculate the work as all of this area under this curve all the way down to the axis, and then when you return on the other side of the cycle on B, the work is going to be this area, and you'll notice those are going to be different values. They're going to be different values by the quantity that is enclosed in this loop. So this enclosed in the loop amount of work is going to be the net work that this cycle results in. And that work could be positive or negative. In this case, the purple area is a large negative work because we have the volume increasing, and then the red area is a smaller positive work. So a big negative number minus a smaller positive number means that the overall work in this system is going to be negative also. It's going to be negative the value of this green area basically in the graph. So this is a system that's producing work. How does this not violate conservation of energy? Well, however much work is being produced by this system is compensated for by an equal and opposite positive Q. So this particular cycle is absorbing heat and turning it into work. This is known as a heat engine. It's a very useful process in the real world, right? We can basically heat things up and get mechanical work out of them. Of course, we could run this cycle backwards. We could have done the B part first and then the A. And if we do that, then we actually flip the signs on everything. We would end up with a large positive work and a smaller negative work. A large positive work on one side of the cycle, a smaller negative work on the other side of the cycle. So the net work in that case would be positive, which means that that system is going to have a net negative Q. Why would you ever want to put work in and then suck heat out of the environment? Well, that happens all the time in our refrigerators. So they actually have moving parts that turn that physical movement into the ability to suck heat from something that is warm. So anyways, these cycles are very useful in either direction. Sometimes there are multiple different pathways, so not just one loop on the cycle, but a number of ways you could get from one spot back to itself. And each one of those pathways is going to have benefits or disadvantages. Some of them are going to produce more work. Some of them are going to suck more heat out or require more work, or, you know, a variety of different things depending on the areas under the curve. So often the questions in the AP test are asking you to evaluate the benefits or challenges of specific cycle pathways. One cycle that isn't really covered specifically on the AP test, but we will talk about it because it's an incredibly common and useful one, is known as the Carnot engine. A Carnot engine cycle is a very efficient way of transforming Q into W, because as far as building a machine that can do it, it's very easy, relatively speaking, to build a machine that can follow this Carnot cycle. So there's 4 thermodynamic processes in the Carnot cycle. 2 of them are isotherms, so the processes bound by those lines T1 and T2 are isotherms, which means those processes happen at a constant temperature. Sometimes those parts of the cycle are called heat reservoirs or heat sinks, and I can show you on the Carnot, on the little Stirling engine I have at school, how we kind of keep 2 parts of our system at constant different temperatures. The other 2 cycles, the ones represented by, you know, the numbers 2 to 3 or 4 to 1, are adiabats. So those are parts of the cycle where the temperature actually changes rapidly as the pressure changes quickly also. Those parts of the cycle basically are designed to get from one isotherm to the next. So the Carnot engine, you could calculate the amount of work by the area inside that curve for the Carnot engine. There's many other examples of heat engines in the real world, but I'm going to save most of those for when I come back to talk to you in a couple days. But if you'd like to see a video of a Stirling engine working, you could click on the link below. Steam engines are another lovely example. I'm sure you can find a ton on YouTube if you want. They use water that they heat up to push the piston around and help contribute to that cycle. So in any case, we'll be talking more about engines. That is going to be it for this lecture, and hopefully you guys can get some practice and talk to each other and get some help from your neighbors, and I will be back on Wednesday to answer any questions that you guys might have. Hope you had a great weekend. Bye.